Professor Andrew Sills from Georgia Southern University, who will speak about using number theory and optimization, combinatorial optimization, to prove an intriguing problem in statistics. Just a note, you can have, you didn't start time yet. Drew was the co-founding, together with me, the co-founder of this famous seminar back in 2003, which is 15 years ago. So we all owe it to and it's a pleasure to have him again. As usual, we're going to take the speaker to dinner. I need to know. So please let me know as soon as the talk is over when we can come to dinner at the usual place, Evelyn's Restaurant at 6:45. Thank you.
Thanks very much, Ronald. It's a pleasure to be back here at Rutgers and to be speaking in my favorite seminar. So, in preparing for this particular talk, I thought it would be appropriate to take into account various opinions expressed on the famous Jerome-Zeilberger opinion page. And so, of course, one of his all-time great opinions is still like that old-time Blackboard talk. So this is a talk that I've given a version of with slides in a 20-minute session. So, but now this is going to be the leisurely 48-minute or 45 plus epsilon minute talk, so that everything will be slowed down and you can stop me and ask questions along the way, and we'll stop when time's up. Another opinion that that was expressed by Doron was that basically that there are no mathematicians left. When Professor Gelfand passed a few years ago, he was a singleton set in terms of actual mathematicians. I mean, we've got number theorists, we've got combinatorialists, we've got topologists, and algebraic geometers and all that sort of thing. So, taking that into account, I think it's a good idea to sort of spread your wings a little bit and go out into unfamiliar territory. I'm not a statistician, but I collaborated with a statistician for this talk. My main expertise and interest is in partition theory, and as you'll see, there are some partitions in here, which is why he brought this to my attention in the first place. So my collaborator is Charles Champ, who is a professor of statistics, the senior statistician in my department. His office is right down the hall from mine. All right, so statistics. So in probability and statistics, one of the things that one does is one gathers data to estimate what certain population parameters are. And so we all know from our elementary statistics course that there's the population mean, and that measures as a measure of central tendency, and then there's the population variance, or its square root, the standard deviation, that measures how spread out the data is. So if we're in a situation where we either know or can safely assume that the underlying population that we're interested in, that we're drawing our data from, is normal, and we've got the Gaussian distribution or normal distribution, the mean mu, and some variance squared, and so we've got mu equals sigma minus sigma. And so, of course, you gather some data. Let's say we have a sample of size n, and we're assuming our underlying distribution is normal with some unknown mean and some unknown variance. And so we want to estimate, and we're going to focus on estimating the square root of variance, the standard deviation. So we want to estimate this. So of course the best way to do this, best is a technical term here, meaning minimum variance unbiased. So minimum variance meaning that the variance of the estimator is as small as possible. And then an unbiased means that the expected value of the estimator is the thing that you're estimating. So I think statisticians use the term best estimator that way. So the standard way to do this is, well, if we recall the sample standard deviation, so I guess what k, say, is 1 to n of data, each data point minus x bar. X bar is the sample average. Square that. Divide by -1. Take the square root of all of that. And this turns out to be an estimator, but it's actually not unbiased. This turns out to be a biased estimator for the sample, or I'm sorry, for the population standard deviation. So in order to make it unbiased, we divide through by a bias correction factor called C that depends on the sample size. And I don't remember what C is, so I have it in my notes here. And it's kind of neat, so I'll show you. So it depends on n, and it's the square root of 2 over n minus 1 times gamma of n over 2. It's gamma of n minus 1 over 2. So that's what C. So if you take this and divide it by this, then that gives you the minimum variance unbiased estimator for the population standard deviation. Okay.
But the straightforward, isn't the n-1 already some kind of correction? The straightforward way was divided by n.
Correct.
So previously they had n-1.
Yeah.
And I guess we did this.
So that was the bias correct, that was the bias correction for when you're estimating this way. You need but then when you take the square root, it introduces additional bias that has to be corrected this way.
Okay.
That's my understanding.
Yeah.
Yes.
So it's standard deviation versus bias.
Right. So yes, good point. Okay, so now this looks kind of complicated and convoluted. So there's a couple of statistical practitioners named Grubbs and Weaver who were interested in coming up with another way to estimate sigma, unbiased, maybe not quite minimum variance, but low variance, so it's maybe not best case, but they would sacrifice a little bit of the variance of the estimator in order to have something much simpler to deal with. Like so sort of the first quick and dirty estimate they got was based on the rate.
That's simple enough. Because the C was too complicated for them.
So yes, they wanted something even simpler than that. Okay? So given a sample, so we have our sample x1 through xn, we have a statistic called the range, which you've learned about in your elementary stat class, which is just the maximum minus the minimum among the data. So that is also a measure of spread, but it's a very crude one. And also, I'm just going to mention and sort of admit that I'm going to use capital R sub n to stand for anytime we have we're calculating a range from a sample of size n. So if you have an R4, you have another R4, they're not necessarily the same one. They're from two different samples. So not all R4s represent the same number, but it's just sort of a sloppiness in the notation, but it simplifies a few things. Okay, so if you want to measure so you actually can estimate the sample, estimate the population standard deviation using the range in an unbiased manner. What you have to do is the following. We define the standardized sample range. Call that W sub n, and that's Rn divided by the thing that you're trying, ultimately we're trying to estimate here. And
But we assume it's a normal distribution.
at this point, we're assuming it's a normal standard
So
distribution.
the range is negative infinity to infinity.
No, the range of the sample.
Each sample.
But you can look at the sample, but you have to estimate it. If you have a sample in front of you, then look at the biggest and the smallest.
Right.
Yeah.
And we're going to adjust that number to get an estimate for.
Oh.
Let's see. Okay. So W sub n is the standardized sample range, and so a quick but crude in the sense of this is going to have a high variance, this estimator. Estimator that's nonetheless unbiased. Its expected value is going to be sigma itself. Is the sample range, just pull the max minus the min from your, whatever your sample is, from your data, and divide by the expected value of the standardized range. Now, so this is unbiased, but its variance is very bad compared to the variance of the capital S over C. So, but nonetheless, what we've sacrificed in variance of the estimator, we've gained in this simplicity. I mean, it's just, we're not doing a big complicated calculation like this. Yeah, question?
So, in actually applying that formula, you need to know the expectation value of Wn. So how do you get, so if that thing is supposed to predict sigma, but in calculating that, you have to know the expectation value of Wn, can you estimate that without using sigma in that formula?
That's the nature of this, of an estimator. So what we mean by unbiased is means this expected value has to be the thing that we're estimating. So this is...
But never again is defined in terms of sigma.
Yes.
So it's not circular?
It's... Well, what is... So this is... And so these parts cancel, and then you get the sigma out of it. So, from the estimator that I'm actually interested in showing you, it winds up that in the process the sigmas, the unknown things cancel each other out. So bear with me. Okay. So what Grubbs and Weaver suggested doing was, well, what if we still take advantage of this idea of using the range, which is very simple, max minus min, but rather than looking at the entire sample of size n, let's break up the sample into subsamples, and then take the range of each subsample, and then take a linear combination of those in such a way to guarantee that we are in fact estimating sigma, and that the estimator is unbiased. Find out which particular way of breaking up the sample will give us the best possible estimator of the possible estimator. So this is where the little bit of number theory comes in, because what I'm actually talking about now is a partition of the sample size, the partition of an integer partition of the integer n. So Grubbs and Weaver suggest, and this is from a paper that was published in 1947 in the Journal of the American Statistical Association. They say consider all, not quite all actually, partitions of our sample size n. So I'm going to call my partition lambda. So lambda, so what does it need to be a partition? Well, its parts, let's say it has some number m of parts where the sum of the parts gives us n, and For a partition, we don't care about the order of the parts, so we're going to put a canonical order in none. And one other restriction that we don't normally do if we're talking about the unrestricted partitions of n, we're going to require that each part be at least 2. So when we're talking about unrestricted partitions, we could of course have 1s as parts. But here we want all our parts to be at least 2 so that we have some sense of the measure of spread. Because what are we going to do with the parts? We're going to take subsamples of this size, and if we have a subsample of size 1, then the range of that, the max and the min are the same thing, so the range is 0, and you're not going to get a sense of measuring spread that way in any sort of efficient way. Okay. So when we have this condition, I'll call this partition admissible. So it's one that's so just as a quick review, if we look at the unrestricted partitions as opposed to the admissible partitions of, say, a standard example is 4, because there's not that many of them. We've got 4, 3 and 1, 2 and 2, 2 and 1 and 1, or 4 ones. The only ones of these that would be admissible for the Grubbs-Weaver problem would be those two. They don't have any ones in them. Now, to set up something I'm going to be doing shortly, I want to give sort of the other notation for these partitions. And that is, we let f sub I for a partition lambda denote the frequency of the part I, so the number of times I appears as a part. So in general, I'm going to use an angled bracket. I'm going to use parentheses when I'm writing the partitions by literally writing their parts. I'm going to use an angled bracket when I'm going to use this frequency superscript notation. So we could also say, since the order doesn't matter of the parts, we can say, well, there's F1 1s, there's F2 2s, F3 3s, and so on. This is a standard thing to do. So, and we generally follow the convention that we don't put the superscript 1 in if it's a 1, and if a part doesn't appear, we don't write it at all. So we've got this, a 1 and a 3, a pair of 2s, a pair of 1s and a 2, or 4 ones. Okay, and again, these are the only admissible partitions. Okay, so what Grubbs and Weaver proposed, and so we call this the Grubbs-Weaver estimator maybe, is we're going to estimate sigma, and statisticians usually often put a hat on or circumflex on top of a parameter to indicate that it's an estimator for it. So we're going to look over, and there's a different estimator for each possible admissible partition of n, our sample size, and this will be the range of the sample of size n sub I, where n sub I is one of the parts there. And the a sub I is, these are coefficients chosen to guarantee that our estimator is unbiased. And we can show explicitly what that needs to be in a little minute, or in a few minutes. So in the case of a sample of size 5, we've got 2 admissible partitions. So what you would do is you would, and they actually did this, they calculated, what the estimator would be in the case of the partition of just the trivial partition 4 and the trivial partition of 2 2s, calculated the variance of each of those estimators, and saw which one of the two had the smaller variance, and that would have been what we could call, then in this case it'll turn out to be the trivial partition 4. That will be the optimal partition, and so that's the one that you would use, or Grubbs and Weaver would use. So the optimal admissible partition? I don't know. Partition of n is the one in which the variance, over all admissible partitions of n is minimal. Smallest. All right.
Just to make sure I'm,
Yeah.
just to make sure I'm understanding, so you're sort of mixing, you have a sample, so when you're talking about the partitions, you're talking about abstract partitions of some number n, but n is also the sample size. So when you
Correct.
talk about a partition 2 and 1, you're thinking of like cutting up the sample into 2 things, 1 thing, 1 thing.
Right.
But then there could be multiple ways, like how things get distributed among them. I mean, there's an abstract partition of n, and then there's, for this partition, how you choose to allocate the n points.
Oh,
that you're
yeah.
handling.
So the way that we do that is, so here's our sample goes from x1 up to x little n.
Mm-hmm.
So how does our subsample go? If we're using the partition n1, n2 up to n sub m, we take.
Oh, and because they're subsamples, they're all random anyway, so you don't have
Right.
to worry about the ordering.
Exactly.
Oh.
So you just take the first n1 of them, the next n2 of them, the next n3 of them, and then the last n sub m of them. So the order is just determined by how you drew your sample in the first place, which is random from your data set or from your population. So. Yeah, so that was actually the next thing I had in my notes, so you read my mind there. Okay. All right. So now I'm going to show you some notation that Grubbs and Weaver used. So, and this is a very...
Yeah, how do you compute this, the variance? So,
Well, that goes into some details that I really don't have time to go into. But there's you go into the theory of order statistics, where you start out with your sample x1 through xn, and then you order them from x. You renumber them, making x1 the smallest and xn the biggest, and then you can calculate using some basic theory what the distribution of the maximum is, what's the distribution of the minimum, and then the distribution of their difference, and all of that sort of thing. So it's a fairly standard thing.
Drew, let me just follow up on that and ask hopefully an easier question, or at least one that's easier to answer. Like, how difficult of a process is that? So you said you can figure out 4 is better than 2, 2. But I would ask you, what's the optimal partition of 10? How long would that take to crunch out the details?
Oh, well, I mean, if you have your program set up on Mathematica, it doesn't take any time to crunch out these variances. In 1947, it probably took a bit longer.
Okay.
And so actually, let me tell you, before doing this notation, let me tell you the punchline of what Grubbs and Weaver found. They found that, they didn't use this term, but I like it. They discovered the rule of 8s. So what does that mean? That means you use in general, you use as many 8s as your parts of your partition as possible. So if your sample is size 32, 8, 8, 8, 8, that's your best partition. Now, of course, not every n is a multiple of 8, so you have to throw in some 9s or 7s here and there. So if it's 33, then you would use a 9 and 3/8. But and there's also for small n, so I guess if you want to say it's for large enough n, you use as many 8s as possible. If you're talking about small sample sizes n, then I think when n is between 2 and 11, you just don't partition at all. You use the trivial partition is the best. In the case of n equals 12, it turns out 6 and 6 does better than any of the other admissible partitions. So there's little variances in that, but the basic idea is if you have a large sample, you can always include lots of 8s, and you might have to pad with a 9 or a few 7s, to account for the fact that not every n is multiple.
And that's for the normal distribution.
And that's for the normal distribution, right? And that's the only thing that Grubbs and Weaver considered.
Do they have a conceptual reason for why 8 appears?
So yeah, that's actually part of what I worked on for quite some time. What they did was they proved by brute force, by doing computations over every admissible partition for every sample or every n sample size from 2 up to 100. Found out, for once n got big enough, what that all these 8s were showing up, and then conjectured what the rule was for any n bigger than 100 as well. But there's no rigorous proof. There's no attempt at it in the paper, and apparently this result is in certain circles is known and is used and that sort of thing. But as far as I can tell, there's no rigorous proof of it in the literature. And so
for n less than 100, it is probably costly. For n smaller than 100.
yeah, so it's proved by direct computation.
So wherever specific n is the direct finite computation.
Yes.
So now we can extend it probably up to 10,000.
Yeah, so I actually did. Using numerics in Mathematica, I was able to check it up. I think I went as far as maybe 5,000 or so, and it still continued to work. And I was looking for how to prove it rigorously, and I failed. And I think that the reason I failed to do so was because the moments of the order statistics from a normal parent distribution don't have a nice closed form. You wind up taking integrals of exponentials to quadratic powers and some other things like that. And there was just this one little sticking point, this one lemma that if I could prove that, then everything else would work. But I always wound up falling back on just something numerical that didn't quite work out theoretically. Maybe someone else knows how to do it, but I couldn't do it. So what I did was, in order to find something that I could prove, was I changed the problem. And so what I did was, instead of doing like Grubbs and Weaver, considering a normal distribution, I considered, well, what if my sample was from an exponential distribution, and then did the analogous problem. So if x1 through xn is exponential with parameter, say, theta, and so there's different ways to parameterize, but I think this is one of the standard ones. You go through same thing all the way through. Turns out you wound up with a rule of 4s. So the underlying distribution is important here. We don't have a universal rule of 8s. It's dependent on normality. And this is something that I actually was able to prove rigorously. And the key point when I have